So let's start with the preview. So it's very difficult for me, by the way, when you or Corbin ask for questions about applications, to come up with answers, not because there are few applications, but because it's like asking a fish for examples of water, right? I mean, if you're a fish, water is all around you, so you can't really think of examples of water because it's all you do all day. So I find it difficult to answer questions about previews and examples just because it's all I think about all day, so I can't really isolate specific examples. It's like suppose you had like a younger brother asking you for examples. He's learning his times tables, so he says, "Where do you use multiplication?" And you can't answer it because it's like literally everything. So I don't know. Small
I
comment.
just realized something. I've seen this equation before.
You've seen the rocket equation?
Yeah. You know why? Because a Kerbal Space Program.
Good. Okay. So this will be familiar, but I will give a
Just the
preview.
concepts.
Yeah, that's fine. I mean, the concepts are, I think, most of the content here. So the tour of what's going on here is that in a classical mechanics course, so for instance, in the intro honors physics course I teach here, you would derive the rocket equation by considering the difference in momentum after a small time step for a rocket. So you look at a rocket at some time t, and then some later time t plus delta t, and then you compute the momentum in each of those two instances. And we're getting a lot of Slack messages. I assume that's not you. So one uses the definition. I'll use an arrow over a letter to indicate a vector. So for a point mass, the momentum of the point mass is the point mass's mass times its velocity, basic physics. So if you start at a time t with a rocket and its detritus is the word we use for this, the exhaust that it spits out. The rocket and its detritus are both moving with velocity v. So velocity is a direction, it tells you how fast you're moving, so that's a vector, which is an arrow. So the momentum at time t is simply the mass times the velocity. Well, the mass, all of the mass is moving with the same velocity. Both the rocket and the detritus are moving with velocity vector v. So we write p at time t is capital M plus delta M times vector v. Fine. Nothing complicated. Then you look at a later time, t plus delta t. This is the time at which the rocket has ejected its detritus, so you're spitting out some exhaust. So at this time, the rocket is moving at a different speed. The rocket with mass m moves with vector speed v plus delta v, and now the detritus, which has been ejected, moves with speed v plus delta v plus u, where u is usually thought of as being negative. It points the opposite way, right? So if you spit something out, it ends up moving slower than you do, right? Because you're spitting it out, so it's ejected in the opposite direction. So u is thought of as a vector which opposes the velocity of the rocket. Cool. So then we compute the momentum at time t plus delta t. Same rule. We have mass m with velocity v plus delta v. That's the first term. Capital M times v plus delta v. You compute the momentum of the detritus. That has mass delta m and total velocity v plus delta v plus u. Fine. So that's this thing. It's very simple. Just, mass times velocity. It's not rocket science. Actually, it's literally rocket science, but it's not difficult. So then the key step is recognizing that the difference between the momentum before and after this small time step is by the definition of Newton's second law, which you may or may not have learned yet. You may or may not have learned that Newton's second law is the definition of force as something called the time derivative of momentum, the derivative of momentum with respect to time. And people will sometimes write this as ma, but that's a special case. I mean, you should really use dp/dt in general. Ma is the special case when there's no mass flow. So here's the second law. Using that, we write the force as the difference in momentum before and afterwards divided by the time step. And the definition of this dp dt in the second law involves a limit. So the entire purpose of my showing you this preview is to convince you that this notion of a limit is completely central to even the most basic questions you would ask in physics. So the force acting on this rocket is defined by this expression dp dt, which is shorthand notation for the limit as delta t goes to 0 of the momentum at time t plus delta t minus the momentum at time t divided by delta t. That's this whole thing. And then using that on the right-hand side of this equation, taking the difference between the second and first lines, we have, again, a limit as the delta t goes to 0 of this whole quantity. So this step in the derivation of the rocket equation is attempting to find how does the momentum of the rocket change after a very small time step where delta t goes to 0 when it's ejecting some detritus. Okay, so this shouldn't make total sense, but questions on what I've said so far?
I do not have any questions.
Okay. Good. So the upshot of all of this is that when we rewrite the equation I wrote on the previous slide in abbreviated form, so now I'm going to use the notation I introduced a moment ago, dp dt, which is shorthand for this limit, we get something called the rocket equation. So this is usually in physics called a differential equation. Why differential? Because the objects on either side of this equation, which we've used this shorthand notation dp dt, those objects are all limits. And each of those limits is a difference between two quantities, p at time t plus delta t minus p at time t divided by delta t. So this is an equation between limits which are all differences, and the word difference gives us the notion of differential equation. So this is literally, if you are a scientist or an engineer, all you will do all day for the rest of your career is to try to understand and solve differential equations that model various physical systems. So this is, the central idea in science and engineering is that of a differential equation. And all a differential equation is an equation between different limits. That's the point. So one other comment is that I'm not saying this is true of you, but many beginning students, when learning limits, get this kind of arrogant attitude where they say, all I care about are polynomials. Like, I don't know, all I care about is things like x cubed plus 3x squared plus 1. And they say, well, I know that we've proven, for instance, that the limit as x goes to some number a, now my pen's broken. There we go. The limit as x goes to some number a of this polynomial is the same as what you would get by plugging in a. 3a squared plus 1. So sometimes beginning students will say, if I only care about polynomials, I don't need to learn all of these complicated properties of limits, because a limit is really just the same as plugging in the number to some equation if I'm restricting to polynomials, because that's all I care about. So people say this, and then they ignore all of the important details about limits, and then as soon as you try to learn physics, the first thing you write down is a differential equation, which is an equation for a limit, and you will notice that if you try to plug in delta t equals 0 in this limit, you get p of t minus p of t divided by 0, which is 0 over 0. So if you have this arrogant attitude that I don't care about limits because I only like polynomials, then the moment you try to do physics, you're kind of stuck, because the most basic thing you could write down, a differential equation for a rocket, for instance, gives you a limit of a quantity which is 0 over 0. So all of the, what seemed like very strange functions that we've been talking about that don't have limits or have kind of counterintuitive limits at certain points because numerators and denominators are both 0 or something, they may seem like outlandish or, I don't know, very strange functions to consider. So you might have thought, I don't care about those functions, I only care about polynomials, but you should not have that attitude, because every derivative, which is basically every application of limits to physics, will be of the form 0 over 0, so you have to be careful about taking limits, because you cannot simply plug in delta t equals 0 and get some number 0 over 0, which is ill-defined. Okay, that is a rant, but questions on this?
I have no questions.
Okay. Good. Okay, so that was my attempt at a preview. So now let's actually go back to doing limits properly. So we remember that the definition of a limit involves this universal quantifier, sometimes written with an upside down a for all. So I just want to kind of build intuition for what this quantifier does in the structure of a proof. So if you want to prove any statement that involves this universal quantifier for all x, something is true for all x, the structure of your proof is always the same. You begin by saying that there's some arbitrary x that was given to you, and then you prove that that statement is true for the arbitrary x. So that sounds very abstract, but we've actually seen this before. So, for instance, if you want to show one subset or one set is a subset of another, we always start by saying let lowercase a be some element of the first set, a. So this is the taking an arbitrary element x as given. So when we proved one set is a subset of another, you always start by saying let a be an element of a, and then you prove a is an element of b. And if you prefer, you can think of this as saying, well, every time a is in a is in b, and you can kind of wrap this all with a, for all a, if you like. So this is how you prove something is true for all x, right? You start with an arbitrary element, you prove it's true for the arbitrary element, and then you think of kind of wrapping that whole argument in a for loop. So that's what we did with subsets, just some kind of cute toy examples that you would discuss in, say, a philosophy course. So in philosophical logic, the first thing you try to prove is, you say something like, all men are mortal, right? So to write a proof that all men are mortal, what you would do is say, this statement mathematically is, for all m in the set of men, m is mortal, right? So for every element of the set of men, that element is mortal. How would you write a mathematical proof of that if these were well-defined mathematical words? You would start by saying, consider a man m, just like we said, let a be in a. So you would say, consider a man m, and then you would prove that man m is mortal. And then you would think of wrapping that entire argument in a for all men m. The argument applies to every man, therefore every man is mortal. So, just toy example. Another toy example, if you wanted to prove there is no person, no one loves everybody. If these were well-defined mathematical statements, and you wanted to prove no one loves everybody, you would start by saying, let H be a human. You're trying to prove there is no human which loves every other human. So you have to show for every human H, there exists a human H prime, so that H does not love H prime.
The problem with this is Mr. Rogers exists.
That's true. Well, he's dead now, right? So our theorem is still we are saved by death. But yes, so, the point of this example is that the claim no one loves everybody is really secretly a for every style claim. For every human H, there is another human H prime, so that H does not love H prime. It's logically equivalent to the original statement, right? So you could say the same thing if you wanted to prove that for every integer n, there's another integer m greater than n. So there's an integer m such that m is greater than n. If you wanted to prove that, you want to prove it's true for every n, so you would start by saying let n be an integer, and then you would need to prove that there's some m which is greater than n. So for instance, you could just define capital M as lowercase n plus 1. And that applies for every n, so your argument is true in general, right? Okay, so I realize I'm beating a dead horse, but questions or thoughts on the idea of for all?
I do like that you're making it sufficiently clear what is going on here.
Well, yeah, I mean, you're going to be angry on the next slide because I have 4 more examples that are still beating the dead horse, but go on.
Are they humorous examples?
Some.
Good enough.
So, okay, so
I have no questions.
You started to say this was sufficiently clear, though, so what were you going to say after that?
I said that.
Oh, so that was the end of the sentence, you're saying?
Sure, I don't know. If I can't remember what I said like 20 seconds ago, then sure.
Okay, well, alright, I will continue beating the dead horse then. So,
whoa.
Alright, if you wanted to prove for every positive real number x, so every positive real, there exists a real number y with the property 2 raised to the power y equals x. So you want to prove this statement. In particular, you want to prove this statement is true for every x. The way you prove that is to begin by saying let x be a positive real. So in the general scheme, you're assuming the element of this quantifying set is handed to you. Someone hands you an x, and then you show how to prove the claim for that x. Right? So if someone hands you an x, you have to show how to find a y with this property, 2 to the y equals x. I mean, we already know how to do that. You just take the log of both sides, the log base 2. So we know how to prove that there is such a y. Y is the log base 2 of x. But the structure of the proof is always to begin by saying, suppose an element of the quantified set is handed to me, and I solve the problem for that example. And then the same argument applies to every element in that quantified set. So, good. That's one example. Another, a kind of humorous, this is probably not true. I mean, I don't think this is a true statement, but I mean, if you wanted to prove it anyway, to prove the statement everyone loves someone, which is the statement, for every human h, there exists a human h prime such that h loves h prime. If you wanted to prove that, you start by saying let h be given, so let h be a human, and you write a proof that there exists a human h prime such that h loves h prime. I mean, this is the hard part, because I don't think that's actually true. It's probably not even true in general that h loves h, but I mean, it's neither here nor there, I guess. So, I mean, the structure is the same. So, another example. So, if you want to prove for every complex number z, there exists a complex number w with the product zw being real. Again, you always start by saying, you've handed me some z. I'm going to prove it's true for every z. So you've handed me a z, and then you prove that there exists a w with the product zw being real. So for instance, you could let w be the complex conjugate. So zz bar is always a real number. Same thing. Last example, if you want to prove that for every positive integer n, there's a real number smaller than 1 over n, again, you always start by saying, well, you give me some n, so let n be a positive integer, let n be an element of the set I'm quantifying over, and then you prove that there exists an x smaller than 1 over n. So, I mean, many different examples, but the structure is always the same. If you prove something is true for every element of some set, you always start by saying, give me some element of the set, and I show you how to prove the statement for that element. Good. Thoughts or questions on this?
This is clarifying things very quickly.
Okay, good.
Also, a quick question. Is every single complex number of the form AB plus CI?
Let's see. You said AB plus CI, you said?
I think that's the right form.
Uh, I mean, you don't need a product here. So, I mean, this is true just because every real number can be written as a product of two numbers, but you can be a little more simple and just say every complex number is A plus BI, where A is a real
Ah,
number
right.
and B is real.
I don't know where that B came. Yeah,
Yeah,
yeah.
that's fine. Yeah, this is actually the definition of the complex numbers. It's
Okay.
pairs.
I
Good.
was just curious if any were weird.
Alas, no. You know the definition of complex conjugate, right? Of Z bar?
I don't believe I do, actually.
Yeah, another travesty. So, if Z is A plus BI, the complex conjugate is simply what you get by reversing the sign on the imaginary part. So Z bar is A minus BI.
Oh, I've talked about this. It just hasn't been of that form.
Ah, okay. So you recognize it kind of.
Yeah.
Okay.
I mean, why did I say form? I meant to say I've never heard the word conjugate used in math.
Oh, so the term wasn't used, but you've used the idea of reversing the sign of the imaginary part.
Yeah, we've said on a few occasions that for every A plus BI there exists A minus BI. Yeah.
Yeah, that's good. I mean, the reason this is useful is that if you multiply a number by its conjugate, you get A squared minus ABI plus ABI, so those cancel, and then the last piece is BI times minus BI, which is plus B squared. So this is always positive, well, non-negative. So the entire reason a conjugate is useful is because if you multiply a number by its conjugate, you always get a real number, and you always get something which is non-negative. That's the point. Okay, other thoughts?
I have no other thoughts.
Okay, this has been, I apologize again for the long build-up, but why am I saying all of this? So the definition of a limit, which we're trying to understand, also has that same structure of all of those examples. It has a for all epsilon greater than 0. Just like, for all humans there exists another human that that human does not love, whatever. So if you ever want to prove that a limit exists, if you are asked to prove a statement with this form, you always have to show that the definition is satisfied for any epsilon, which is why you always start by saying let epsilon greater than 0 be given, and then you construct an argument that gets a delta, it builds up a delta, so that this sentence, this long implication is true. So the point is that you always say let epsilon greater than 0 be something which, this is the set I'm quantifying over. This is any real number epsilon. And then you show that this statement is true. So you can find a delta. So in particular, if you write a proof that starts with saying let epsilon greater than 0 be given, and then in a later step you choose a value of epsilon, like you say epsilon equals 5, then that's not going to work. You can't write that and then at the end of the day go back and kind of wrap your argument in a for loop for all epsilon, your argument that you wrote down there. Because if somewhere in the argument you chose a value of epsilon, then it's not going to be true that you can iterate and write a for loop over all epsilons, because it only works for one value of them, right? So you can't pick the epsilon. It has to work for all of them. Okay. Silly
So, I think what got me hooked up this entire time was that I was reading let epsilon greater than 0 be given, as in given is in the definition of limit, but not like you are literally handed an epsilon and it has to work for all of them.
Hmm. Yeah, this is perhaps confusing terminology to use. So given means that it's chosen by someone else or handed to me, right? So this is the same as when you prove subset equality, right? So if you want to prove A is a subset of B, you say let A be an element of A. So when you do that, you're assuming someone hands you an object, and all you know about that object is it belongs to A. You don't know jack shit about it. It could be a number, it could be a matrix, it could be a function. All you know is it belongs to A. And you have to write the proof knowing only that it belongs to A. That's what given means. In the same sense, let epsilon greater than 0 be given means that someone hands you an epsilon, all you know about it is it's greater than 0, that's all. And you have to prove that this junk is true for that epsilon. Good?
Yes.
Okay. All right, so now I will work through the 1 over x example for you, which you said you have not finished yet, but hopefully after going through this, you will be able to finish it. So the goal is to prove that this limit exists. The limit is x goes to a of 1 over x is 1 over a. I think you've spent plenty of time doing the exploration for this proof, so I will skip the exploration and just write the final polished argument so you can see how the steps work. So here's the argument. Now remember, this statement that this limit exists is a for all statement, so for all epsilon. So our proof that shows that this works for any epsilon better start by saying let epsilon be given and then show how to prove the resulting absolute value junk given that epsilon. So that's what we'll do. We start by saying let epsilon greater than 0 be given. I have to show you there exists a delta. So I'm going to skip all the exploration and just write down the answer. This is the thing which, if you go through all the steps that Spivak scaffolds for you, this is the delta you will end up picking. It's the smaller of absolute value a over 2, and epsilon times the absolute value of a squared over 2. Notice that delta should usually depend on epsilon, right? You're just showing that if you hand me epsilon, I can find a corresponding delta, but usually I'll pick a different delta if you hand me a different epsilon. So if your delta doesn't depend on epsilon, usually something's wrong, unless it's a constant function or something weird. So this is the choice. And then all we have to do to prove the limit exists is to show that this choice of delta satisfies the definition. What's the definition? If 0 is less than the absolute value of x minus a is less than delta, where this is the chosen delta, we have to show that the function f of x minus the limiting value, which is L, in absolute values, will be less than epsilon. So that's all I have to prove. This will be the content of the proof, is proving that if you use this delta, this will be true. And I'll do that in 2 slides, which you've worked through most of the algebra of, but the 2 steps are showing first that if x is within distance a over 2, which is implied by this statement, if x is within distance delta of a, and delta is the smaller of these 2 numbers, then x is certainly within distance a over 2, absolute value a over 2 of delta, because it's within a distance which is the smaller of these 2. So the first step is to use that assumption to prove a nice inequality, and the second is to use that same assumption to prove that the difference of interest is less than epsilon. So I'll do those in the next 2 slides, but thoughts on the structure or the plan so far?
So I've done all the algebra, but I haven't gotten anything similar to what you have defined in delta equals minimum of those 2.
Right, so you chose the first part, right? You started
Okay.
writing a solution and you said, well, I think you wrote, you want x minus a to be less than a over 2, right? You wrote this and probably 0.
Yeah.
So that's the first part. You're saying, delta has to be at most this thing. You did that, and then you use that to show that if you make this assumption, x will never be 0, which is nice, because you won't divide by 0. But then you never got to the last step where you say, if you hand me an epsilon, I can make this difference, 1 over x minus 1 over a, less than epsilon. Right, so this thing, just like when we did x squared, right? Remember when we did absolute value of x squared minus 4 or something, right? And you factored it. You said this is x plus 2 and x minus 2. You made an initial assumption that x was between, say, 1 and 3, and you use that initial assumption to bound the hard term, x plus 2. So there was an initial assumption, a restriction on delta. The thing you wrote down in your solution was just the initial restriction. It's the analog of the restriction that x be between 1 and 3. So that's good, it's half of the solution. You need the initial restriction to handle the complicated term, but you also need the second piece that makes it less than epsilon. Does that make sense?
Yes.
Okay. Other questions on this slide, or should I go on?
I believe you can go on.
Good. Okay, so what are the steps? First step, I mean, you've seen this algebra, but this was trying to show this thing about 1 over x, that it's less than 2 over absolute value of a. So we assume this is true, which is the initial restriction. You assume that absolute value of x minus a is less than absolute value of a over 2, and you did that in your solution. What does this buy us? So Spivak, in a very cheeky way, I think in the text he says by, I don't know, he picks some, he says we proved in exercise 1.12 or some number that this is true, but he doesn't say reverse triangle inequality. It's very cheeky. If you're reading quickly and not paying attention, you won't notice it. But Spivak uses the reverse triangle inequality, which is this thing. If you have two numbers y and z, their absolute value, the absolute value of their difference, y minus z, is lower bounded by the absolute value of z minus the absolute value of y. So we use that here with, just plug in y is x and a is z. So you make this pairing, and then you have z is a, so the left side is absolute value of a minus absolute value of x, which I've written here. That's less than the absolute value of x minus a. We already know that's less than the absolute value of a over 2, so I chain those inequalities here. And then I just add x to both sides to move the x to the right, and subtract absolute value of a over 2 from both sides, which leaves me with absolute value of a over 2 on the left. So that gives me this line, and then you can simply raise both sides to the power minus 1, which flips the inequality and gives me this line. So I think you understand this because you worked through most of it, but are there questions on any of these steps?
I don't actually think that I did some of these steps, unless I'm just have terrible memory somehow.
I think you got to this one. You didn't invert, if I remember correctly, but you got halfway through or so on, something like that.
I don't remember the reverse triangle inequality bit, actually.
Yeah, I think...
I have no idea.
Yeah, I don't know. I mean, I think when you read the Spivak, the reading for one of the daily challenges, you said, I understand the step because it's the triangle inequality, but you didn't comment on the fact that it was the reverse triangle inequality. So maybe you were just reading hastily or something.
Thinking.
Woo.
Yeah. Okay, well, I will go on since I think we're happy. So that was step 1. Now we do step 2, which is concluding the proof. So again, we're trying to prove this implication that if this is true, then it implies that the absolute, well, f of x is 1 over x. I'll just be very explicit. 1 over x minus 1 over a is less than epsilon. That's about epsilon. So we're trying to prove this. So to prove that this implies this, you assume the first thing is true and show the second thing is true. So we suppose 0 is less than the absolute value of x minus a is less than delta, which is, again, the minimum of these two things. This is very important. So if a number is less than the minimum of two numbers, it must be smaller than each of those two numbers separately, right? Because the minimum is simply whichever of these two is smaller. So if this thing is smaller than whichever of these two is the smaller, it's smaller than both of them. So if absolute value of x minus a is less than absolute value of a over 2, we saw in step 1 a second ago that you proved this thing by inverting. You got some inequality and then flipped both sides. So this is true, and also this is true, because this is just the second component of the minimum. So the two things are true. Now all we have to do to prove the claim is show that if these two things are true, then the conclusion in the definition of the limit is true, this thing. 1 over x minus 1 over a, absolute value is less than epsilon. And this algebra I know you've done. So you take this thing, multiply both of these fractions by 1 in a particular form. So this is, a over ax, and this is x over ax, and then you reverse the sign, so this is the same as x minus a over ax. And then you use that the absolute value of a product is the product of the absolute values to split it like this. And this is the key step. We use the two assumptions we found above to conclude that these factors are all upper bounded by certain numbers. So the whole point of step 1 was to handle this factor here. 1 over x is less than 2 over absolute value of a. So this factor here, 1 over absolute value of x, is less than 2 over absolute value of a. The whole point of this restriction was that we can handle this factor. Absolute value of x minus a is less than epsilon absolute value a squared over 2. So we use both of those, and now you can kind of see how the cancellation will work. If you replace each of these factors by the thing it's upper bounded by, you get epsilon absolute value of a squared over 2 times 1 over absolute value of a, which kills one of these factors, times 2 over absolute value of a, which kills a second factor, and kills the 2. So these were carefully chosen so all the factors would cancel, and we'd be left with epsilon, which is exactly what we wanted to prove, that this thing has been made less than epsilon. Punchline is that for any choice of epsilon, we never picked a particular number, like epsilon equals 5. We never said that. For any choice of epsilon, we can make this choice of delta, and then the implication in the definition of the limit will be true. That if this is true, then this is true. So that's how an epsilon delta proof works. Questions on this?
In those 15 minutes, I think it was, I suddenly understand limit proofs a lot better.
Okay, good. I realized I probably went too fast.
Stopped messing around with my lighter.
Wait, what? You have a lighter that you're playing with?
Yes, I don't know why, but it was in a drawer, and I'm like, oh, this is cool.
Not bad. Okay, are you happy? Well, do you think that you are now able to write up the solution for this proof in the consolidation document correctly now?
Yes.
Okay, good. I think I have some more. Okay, I'll do this quickly just to emphasize that the problems we've done before are really the same strategy. So what we saw last time, for instance, was this proof that the limit as x goes to 2 of x to the power 4 is 16. And up to modulo the typos, the argument was let epsilon greater than 0 be given. So you hand me an epsilon. I can pick this delta, which is the smaller of 1 and epsilon over 65, where here the 1 is chosen so I can restrict one of the factors when I factorize this thing. So if delta is the smaller of these, and we assume that the absolute value of x minus 2 is less than delta, so it's smaller than both of these in particular, we need to prove that under that assumption that the absolute value of f of x minus L, which is this thing, is less than epsilon. And as we saw last time, we can prove that kind of just by algebra. So since absolute value of x minus 2 is less than delta, which is the smaller of 1 and epsilon over 65, in particular it's smaller than 1 because it's smaller than the minimum. So if it's smaller than 1, x is between 1 and 3, as you told me in the last meeting. So this product is upper bounded by 5 times 13, which is 65. So that's using the initial restriction. Then we use the second restriction that also absolute value of x minus 2 is less than epsilon over 65, the second restriction. And to use that, we factor this expression, which we want to show is less than epsilon. So this thing is x squared minus 4, x squared plus 4, which is x minus 2 times x plus 2 times x squared minus 4. And this is where we use the two assumptions. That here in this step we proved that this is smaller than 65. And by assumption, we chose absolute value of x minus 2 to be less than epsilon over 65. So again, they were precisely chosen to cancel, so this would all be less than epsilon. And that whole argument works for any choice of epsilon. Give me any epsilon whatsoever, and I can define this delta so that this whole argument goes through. So we can wrap the whole argument in a for all, if you prefer. There's a around this entire argument, so for all, well, maybe for all epsilon greater than 0, the argument goes through. That's the point. Again, beating a dead horse, but questions or thoughts on this?
No questions or thoughts on this specifically, but your dots look like a frowny face of sorts.
Oh, you're right. It's a long frowny face.
Why do I notice these things?
It's kind of a almost a, I don't know.
Yes!
There we go. This one looks more frowny because of the way I drew it by accident. So I don't know. This one looks just like, I don't know, confused or indifferent. Okay.
Observations of lines, woo.
Onward. Okay, so let's try to apply this. This is 10.1, which is one of the things due midnight tomorrow. So I've scaffolded it for you here in 3 steps. So the statement, well, maybe, I don't know, I'm sick of my own voice. Can you read the statement of the challenge for me?
Oh wait, my mic was unmuted. Whoops. Challenge. Suppose f is a real valued function with f of x, the absolute value of f of x is less than the absolute value of x, where all x in the real set. Real? Question mark? Cool. Prove that f is continuous at 0. Number 1. What is f of 0? Number 2. What must we prove to show f of f is continuous at 0? Should I just keep reading?
Yeah, go on.
Okay. Question 3. If someone hands us an epsilon and asks for an interval of x values for which it is guaranteed that f of x is less than, that the absolute value of f of x is less than epsilon, which interval should we choose?
Good, okay. So the easiest one, I guess, the first question, I claim that this bound, that the absolute value of f of x is always less than or equal to, the absolute value of x, typo. This uniquely determines the value at f of 0. I claim that if this is true, then f of 0 can only be one thing. What is that one thing?
Sorry, read it. Yeah. Say the question again.
So if for any x, the absolute value of f of x, the output of f at x, is less than or equal to the absolute value of x, what can we infer about the output at 0, f of 0, based on this assumption, this inequality?
F of x equals x at 0?
Yeah, so at 0 in particular, what does that mean f of x is equal to when, well, let me be more explicit. So what is f of 0 then?
0.
Yes, good.
Oh.
So that's the only...
Well, that's just...
Yeah. Okay, so that's the first part. Good. So now if we want to prove f is continuous at 0, what must we prove? What is the statement that we have to establish to show f is continuous at 0?
We must... Yep, my mic is on. Oh, by definition of continuous, we had to show that the limit of f of x as x approaches 0 is equal to f of 0.
Yes. So the limit as x goes to 0 of f of x equals f of 0, which happens to be 0. So we have to prove this, which again is a for all. I mean, this unpacks into the statement that for all epsilon greater than 0, there exists delta greater than 0, so that the absolute value of x minus 0, which I won't write, absolute value of x, well, so that 0 is less than the absolute value of x is less than delta, implies the absolute value of f of x is less than epsilon. So that's what we have to prove. So I've converted that into English in the scaffold question 3. So if someone hands you an epsilon, which is the statement of for all epsilon greater than 0, someone hands you an epsilon and asks you for what interval of x values, so for which choices of the input x, will it be true that the absolute value of f of x is less than epsilon, and possibly using this assumption, what interval of x values should you take? Which should you pick?
I'm in deep thinking. I feel like the interval we should choose is it going to be the, I don't know if it's going to be open or closed. So I'm just going to say closed because that just, I think, yeah, that's going to work regardless.
Well, less than, right? So it should be open.
Oh, right. Okay. I guess the open interval negative epsilon over 2. That's a total negative epsilon over 2, epsilon over 2. But that doesn't feel quite right at all, so.
It works. It's stricter than we need, but it works. So if you take, let's prove why this works. So suppose x is an element of this open interval from epsilon over 2, minus epsilon over 2 to epsilon over 2. Then what do we know about f of x? Well, the absolute value of f of x, by assumption up here, this kind of key assumption we made about the function, this thing will be less than or equal to the absolute value of x. But since we've chosen x to lie in this interval, everything in this interval has absolute value at most epsilon over 2 because of the way you've constructed it. So this thing is less than epsilon over 2. So you've won the game, since the question was pick an interval of x's so that the absolute value of f of x is less than epsilon. You've won handily because for all of your choices of x, the absolute value of f of x is smaller than epsilon over 2. It's even stronger. Less than epsilon over 2 is a better bound than less than epsilon because, half epsilon will always be smaller. So, yes, that
But
works.
I could have used epsilon, right?
Yeah, that's fine. I mean, but this is why I asked about Spivak's comment about being economical. You don't have to be economical. You can pick epsilon over 2 if you want. It still works.
Epsilon over 90,000.
It's over 9,000! Good. Other questions on this?
I have no questions.
How long? That doesn't actually...
Look at all that drawing.
5:45. Oh, we're only 1 hour in. I feel like... Yeah, okay. I'm starting to worry that I had gone too long, but... Okay, good. So... That... Well, let me write the solution more carefully. Mine uses epsilon rather than epsilon over 2, but that's fine. So the first step was showing that f of 0 must be 0, which I think you understand, that the absolute value of f of 0 must be at most 0, which is, kind of only allows one thing. So then we have to prove that the limit as x goes to 0 of f of x is 0. And as you say, if you suppose someone hands me an epsilon, let epsilon greater than 0 be given, then we can choose For instance, delta equals epsilon or delta equals epsilon over 2 also works, or delta equals epsilon over 90,000 also works. Any of those choices will have the property that when the absolute value of x is between 0 and delta, then using this definition, the absolute value of f of x will be upper bounded by delta and therefore also upper bounded by epsilon, using that assumption. So the whole point is that in this proof, we said, suppose you hand me an epsilon, here's how I pick a delta, which happens to be equal to epsilon, and that proves the claim for the epsilon you handed me. It's true generally. So because this works for any choice of epsilon that you hand me, I can wrap the whole argument in a for all epsilon, which proves that the limit exists. The limit as x goes to 0 of f of x is 0, and therefore f is continuous at 0. Good. It's short proof, but I think conceptually rich. So questions on this?
It might be a bit of an ask, but are you are you uploading these slides to Piazza? Just curious.
Yeah, I think I might have forgotten to put the last set of slides up, but I can definitely put these on after we're done talking. Sure.
Yeah. Just checking. I'm good with this slide.
Sweet. Okay, what else? So now, and the preface for this set of questions is because I think often students, when they're given definitions, will memorize the specific choice of letters and phraseology in the definition. So they memorize kind of the surface details rather than understanding the deep ideas and actually understanding what is this definition doing. So to discourage you from doing that, I will give several alternate definitions of the limit. Some of these alternate definitions are logically equivalent to the original one, which means that whenever this new definition holds, the old definition holds, and vice versa. So they're exactly the same. So for some of these they'll be the same, for some of these they will not be equivalent. And your job is to disentangle what are the kind of unimportant surface things I've changed about the definition, and what about the important ideas I've changed, and tell whether they're the same. So, okay, so the first one is, I'll just tell you whether it's equivalent or not. So the challenge is explain why this different definition of the limit is logically equivalent to the usual one. So this one is the same. And the definition is, we define the limit as x goes to a of f of x equals L as the statement that for every delta greater than 0, there is an epsilon greater than 0. So notice that we've switched the order of these from the way they usually appear. There is an epsilon greater than 0 such that for all x, if 0 is less than the absolute value of x minus a is less than epsilon, then the absolute value of f of x minus L is less than or equal to, now an equal to sign, 5 delta. So think about that for a moment and see if you can explain why this is still logically equivalent to the original definition.
Well, I know that the different order of for every delta greater than 0, there's an epsilon greater than 0. That is still equivalent because epsilon and delta are just, what's the proper name?
Dummies.
I'm just going to say dummy variables, placeholders, etc.
Yeah, so I'll just go ahead and replace those because these are dummies. We can call the dummies whatever we want, so I agree. So that change is not meaningful at all. We can change the dummies to be whatever we want. So what about the other change that 1, we've replaced this with a less than equal to, and 2, that it's a 5 epsilon instead of epsilon.
Okay, so the first statement, if 0 is less than the absolute value of x minus a and absolute value is less than what is now known as delta, because we are referring to what we know. I don't even know. That's still the same. It's acting as a restriction on the domain. Is it wait. Yes.
Yeah.
I've never thought of this before. That's still, this statement is acting as a restriction on the domain, right?
Yeah, this is picking out a subset
Okay.
of the domain from, say, a minus delta to a plus delta. Yeah, sure.
Okay. Just verifying for whatever reason. Yep. And considerably less rigorous. I don't believe that the height of the vertical, like the restriction on the range of this function, quotation marks. I'm thinking. I don't believe that a wider range is going to have any effect because,
Yeah, I don't know how to word this part.
Okay, so you're saying the fact that it's 5 epsilon rather than epsilon here should not change the statement. So why is that? I mean, naively you would say, 5 epsilon's a lot bigger than epsilon, right? So if this is 5 epsilon in either direction, then why is the statement of the definition of the limit unchanged by that scaling?
because our restriction on the domain only cares about the let's think about how to word this again. It only cares about the stuff that's within the vertical range of the domain's counterpart.
I'm not sure I understand that sentence. So
Yeah, that was butchering.
I think the reason it doesn't matter is because of the for every. For every epsilon greater than 0, this is true. So,
Blue.
in particular, suppose I wanted to pick a delta to guarantee that the output was in, some distance, maybe 1/1000th of the value L. So, with this new definition, it seems like I would kind of pick, I would make my epsilon be 1/1000th, and then this definition would tell me that, well, your output will be within 5/1000ths of the target value. So naively it seems like, well, this is less precise. If I want epsilon to be 1/1000th, this thing only tells me my output will be within 5/1000ths of the target value. But the key is for every epsilon. So you could just change this and say, well, if I want my output to be within a distance 1/1000th of L, I'll just pick a different epsilon. This is true for every epsilon. I can pick any epsilon I want. So in particular, I can pick something like, I don't know, 1/50,000th. So I pick a different epsilon, and then this definition tells me, well, you will be within 5 times that epsilon, so you'll be within 1/10,000th now. Actually, you'll be less than or equal to at 1/10,000th. So you could be equal to 1/10,000th away from L. But even if you're equal to 1/10,000th away from L, you will certainly be less than 1/1000th away from L. Right, that's what I really wanted, is 1/1000th. So the point is for every, right? If you want, you keep in your head a secret idea of the epsilon you actually wanted. And if that's the epsilon you wanted, since the definition holds for every epsilon, you just divide the secret value you wanted by, 10 or 100 or something. And then this definition, it'll give you a shitty error. It'll make your error 5 times as big, and maybe you'll be equal to that error. But since it holds for every epsilon and you divide it by 10, then your error is still going to be like half of what you wanted it to be. That's why it doesn't matter. Does that make sense?
As I try talking without the mic on, yes.
Okay. Good. So let's see the write-up of this. I think I was a bit cheeky in the solution, but so I try to argue here that the two definitions are the same. So if the definition exists, or the limit exists in this new sense, the new definition, then we want to show the limit exists in the old definition, and the way that I do that is just say, well, let delta be epsilon over 10. Right here, delta and epsilon are switched. So if you let delta be epsilon over 10, this thing guarantees that you will be within half epsilon of the target, which certainly means you'll be within epsilon, which satisfies the usual definition, I guess. So that's good. The other direction is that if it exists in the usual sense, it automatically exists in this new sense, because here, again, when you relabel the dummy variables, this is just 5 epsilon. So if the limit exists in the old sense, this will always be less than epsilon, or delta, since we've changed the names. But it's always true that epsilon is going to be less than or equal to 5 epsilon. That's kind of trivially true. So if the limit exists using the old definition, it also exists in the new definition. So they're exactly the same, despite the fact that they look different. We've changed the letters, we've put a less than equals, so forth. Good. Other questions?
I'm good with this. I do not have any questions. Though, was that honking I heard in the background?
Yeah, there's someone sitting outside my apartment building just leaning on the horn. It's kind of annoying.
Okay, just checking that wasn't your mic just dying on me.
Not that.
That'd be quite an amusing dying, though. Just honk.
The worst kind of dying. Okay, so here is an alternate definition that is not the same. So this definition of the limit will, it will not correspond to the usual one we think of. And your challenge is to decide on why. So I will ask you can you read the whole thing?
I'm sorry. I saw the for all x. Okay. I don't know.
That's funny.
Wait, did you tell me to read it?
Yeah, if you don't mind, could you read the challenge and the definition?
All right. Challenge: explain why this different definition of the limit is not logically equivalent. 1. Limit of f of x as x approaches a equals L. Equal. Implies, defines.
Define, I usually say this, or defined as.
Is defined as. For every delta greater than 0, there is an epsilon greater than 0, such that for all x, if 0 is less than x minus a is less than delta, then f of x minus L is less than epsilon.
Yeah, so what's weird about this?
It's acting as if you are given a delta, and that is, when I'm talking about delta, I'm talking about the restriction on the domain.
Yes. So there's no funny business about changing the dummy variables. It's still delta as the restriction on the domain, as you say, and epsilon as the restriction on the range somehow. But the order of the for all, or the for every, and the there exists has been switched, right? This is saying for every delta, there is an epsilon. That seems really weird. This is not the same as the usual definition of the limit as suggested. So I will ask you to think of an example of a function where the limit, as we usually think of it, does exist, but with this new definition, it would not exist because the definition is just wrong. And the hint is to think of a constant function. So if f of x is always equal to, I don't know, some number a, or I don't know, 1. So if f of x is always 1. So using the usual definition, we would say the limit exists at every point on this constant function, because it's as smooth as you could possibly hope for. But is it true that for every delta greater than 0, there's an epsilon greater than 0, such that this thing is true for the constant function? What do you think?
Let's see. Well, I'm looking at the statement. If 0 is less than the absolute value of x minus a is less than delta. Wait, let me think about this. You cannot choose a delta such that it is greater than a false,
Cannot.
because x minus a, regardless of what you choose for x and a, is going to be 0. Yeah, that was a botched explanation.
You're saying this will always be 0 because it's constant. Or I'm confused.
That as well.
Actually,
Wait,
okay.
what?
Let's,
Okay, now I'm suddenly thinking that limits don't exist on a constant function. What happened?
Okay, let's do a different one. So let's let's think of a limit that should not exist and try to show with the new definition it does exist. Because that'll give us something that's another contradiction, right? So let's think of f of x, I don't know, this is 2 and this is 1. Right? So I mean we should fill in one of them, I guess. So we would usually say this limit does not exist, right? Because the limits as I approach from the right and left are different. So let's try instead to prove that with this new definition, it is true that the limit exists at 0 for this new definition of limit. So can you explain why for every delta there's an epsilon greater than 0 such that this statement is true for the written function f of x? In particular, what is the epsilon?
I ask you this a lot, but can you restate the question?
Sure. So the question is, can you find a choice of epsilon which will make this statement true? And since this statement is the new definition of a limit, that would mean the limit exists at 0 for this function. So can you find a choice of epsilon which would make the limit exist at 0 for this function, which would prove that this is different from the usual definition, because usually we would say the limit does not exist here. So in particular, can you find an epsilon so that this is always true? That the absolute value of f of x minus L, whatever number you want to claim the limit is, that this is always less than epsilon.
Let's just say 2. As.
Sure. Okay, so you pick epsilon equals 2. What L, what do you want to say the limit equals?
Let's say the limit equals 2.
Yeah, now you win, right? With this shitty definition of a limit, it's the game is that someone hands you a delta, so they tell you how close x was to 0. So someone hands you a delta. All you have to do is pick an epsilon so that the output of the function is within distance epsilon of whatever you claim the limit value is. So you say, sure, the limit value is 2. I claim that if you plug in a value of x in this interval, you will always get something within distance 2 of 2. But that's pretty obviously fucking going to always be true. So if you plug in any number whatsoever to this function, you're either going to get 2 or 1. And in either of those cases, you're going to get something within distance 2 of 2. So using this definition, you can prove that the limit exists at any point, and the limit is equal to whatever you want, right? You could have picked something different. You could have said epsilon is 50, and L is 49, and then you would have said the limit as x goes to any point a of f of x equals 49, and with this new definition that would be true. So surely this cannot be the same as the usual definition of the limit, because you can show that the limit is whatever you want, because the epsilon and delta are backwards. Good, okay, so I think you got the point, but questions on this?
I do not have any questions.
Excellent. How far am I? 5:45. Okay. Well, I'll do the last one, and then I think that should be enough. Okay. Well, the explanation... Yeah, I think I used a simpler example with the f of x, which is 1 if you're non-negative, and it's 0 if you're negative, and you could do the same thing. You can choose any epsilon you want, like 5, and then prove that the limit exists. The limit is 0, the limit is 1, the limit is 2, the limit is whatever you want. So this definition could not possibly be the same as the usual definition, because we've proven there can only be one unique limit. Okay, the last one, this one I will not tell you whether it's logically equivalent to the usual one or not, as someone blares stereo music outside my apartment. Okay, so can you read this third possible redefinition of the limit?
Sure. I mean, I kind of have to. Challenge. Is this different definition of the limit logically equivalent to the usual one? More importantly, why or why not? Begin quotes. The limits of f of x as x approaches a equals L. Defined for every epsilon greater than 0, there is a delta greater than 0, such that if the absolute value of f of x minus L is less than epsilon, then 0 is less than the absolute value of x minus a is less than delta.
Good. Notice I feel the need to defend myself about this, but I know that it's grammatically incorrect to put a period outside of quotes. When you quote usual sentences, you're supposed to put the period inside of quotes. But in math, the writing of a statement with a period is different from the writing of a statement without the period. So I have the habit of, when I'm quoting ordinary English sentences, I will follow the grammatical conventions and put the period inside the quotes. But if I'm quoting math, I always put the period outside, because the quotes should enclose the precise mathematical sentence, and the sentence with a period is different from the sentence without the period. So, I mean that's just me. There's no content to that sentence. I'm just trying to convince you that I'm not an uncultured swine that doesn't know how quotes work. But anyway, ignoring that, what is different about this usual what is different about this from the usual definition?
The imply statement has been swapped around.
Yes. So
I'm trying to find the... We went over this in the past, contrapositive, and the other two that I can't remember the names of.
Yeah, so the contrapositive is logically equivalent to the original statement. The others are converse and inverse. This one is the converse. The converse is not always logically equivalent to the original statement, but sometimes it is. So the question for you is this one logically equivalent to the original definition of the limit or not?
I want to say yes, but I can't prove it.
Okay. Do you have an idea or intuition for why yes?
I feel like it is just in the definition of the implies, the if-then statement. I don't know.
Well, let's see. How does it...
No, because... Never mind.
P implies Q.
This doesn't...
P. Yeah, I mean, let's try to find a counterexample of that where implication doesn't usually work. So, M is a man implies M is mortal. Is it true that if M is immortal, a mortal, then M is a man. Is that true? Can I switch the order? That's not how that works because women exist. I mean, you and I may not be very familiar with this statement personally, but women are actually things that exist in the world. So not every instance of a mortal is necessarily a man. You can't simply switch the implication and get something which is also true in general, right? Fuck. So to make this somewhat more clear, the original definition of the limit was saying that we can always get the output of the function. We can always get the output of the function close to some number by taking the input of the function close to some number. That was the usual definition. We can make the output close to a number by making the input close to a number. Here we have reversed the order. We've reversed the order, so now we're saying, can you always make the input of the number close to a particular value by making the output close to a number? So is it always true that if the output of this function is close to, I don't know, 5, if the output is close to 5, does that always mean that the input was close to some, I don't know, some other value, some particular value like 5? Can I always make, am I always guaranteed that outputs which give me 5 for this function will be close to this number 5?
It sounds like it should be true, but that doesn't get me anywhere.
I don't think it even sounds true. What if I plug in minus a billion? 10 to the 9 or something? If I plug in minus a billion, I've drawn this function to be constant. So if I plug in minus a billion, I still get 5. So is it true that the input is always close to 5 if the output is close to 5? I don't think so. I can plug in any number and I get 5, right?
I forgot about the horizontal line test.
Yeah, this is an invertibility problem. So this one is not logically equivalent to the original definition, and here's why. Consider the constant function. So this is the one we were beginning to use in the first example. So consider the constant function f of x equals 1. So we're going to disprove that if the output is close to 1, then the input is always close to 1. But that's very, very simple. Because, if you choose, say, epsilon equals 1, is it true, so that's our choice of for every epsilon, is it true that you can pick a delta, you can pick an input tolerance, so that if I am within that input tolerance of, I don't know, say 1, or any value which gives me 1 from this constant function, if I'm within that input tolerance, then every input which gives me an output of 1 will lie within that interval. Or in other words, can you find any delta so that here's a plus delta and a minus delta, can you find any delta so that all of the inputs which give an output of 1 for this function will lie within that interval? Well, no, you can't find any such delta, because by construction, every output of this function is 1. So you can plug in whatever number you want. So you can never pick an interval big enough, because there will always be something outside that interval. Unless it's minus infinity to infinity, but that's not allowed by our definition of delta. Delta has to be a positive number. It can't be infinity. So that's why this definition doesn't work, because the limit existing is the statement that close inputs give you close outputs. That's not the same as close outputs give you close inputs. You can pick very, very far away outputs and get the same input.